All right, fantastic. Now, I know I got to slightly different ending places with you guys as I did with my other section. I do recall spending 2 minutes two classes ago on why space is a vacuum. I think Henry made me talk about that, right? Did we talk at all about the history of our solar system? I don't think so, right? Okay, great. So who can tell us, right? Who's already learned about this stuff? All right, Henry, go ahead. Tell us about the history of our solar system.
Well, it all started with the Big Bang, which I think, if I remember correctly, was a very, well, relatively speaking, was a small amount of like every single kind of matter compacted into one hot, dense kind of core almost type thing.
And that's what made our solar system?
No, because then it rapidly expanded and all the stuff got scattered all over the place.
Okay.
Then
jump us forward to our solar system.
To our solar system.
Yeah.
Okay. Didn't a star that was near our solar system get destroyed, or it ended its life cycle, and then all this stuff kind of floated around, and then there was extra like particulates, and then that eventually formed planets and whatnot?
So much of what Henry is saying is true. So how about some timing? When was the Big Bang?
2 million.
Way more than 2 billion.
5 billion.
Something like maybe like 15 billion.
15 billion.
All right, so like 15 billion years ago. And what Henry said was basically correct, that all of the matter and energy of the universe was located in a teeny tiny speck of volume, like smaller than the size of an atom, right? So that was not stable. That tiny volume but huge amount of mass did essentially explode and send all of the matter and energy that makes up our universe today in different directions. Fine, right? Yeah. And then how old is our solar system? Because that's what I want to hone in on. Because our solar system is not 15 billion years old. What do we learn in like 7th and 8th grade and 6th grade science? We don't learn science ever. Geology should include this stuff. Rocks, that should include part of this stuff. Alright, so 15 billion for the universe, fine. Give me a guess for the solar system.
5 billion.
5 is not so bad. Might be closer to 6, but fine, somewhere in there. So our solar system has only existed for, roughly a third of the lifetime of the universe. But the matter that makes us up and that makes our solar system up, certainly predates our solar system. Like, you can't create matter. That's a sort of true. So this matter must have existed in some other form, 10 billion years ago, 11 billion years ago. And Henry was again correct that there would have been a previous solar system that held the matter that makes us up now. But stars don't really live forever. Right? In fact, our star, the sun, is about middle-aged. So even though it's only like 5 to 6 billion years old, right, it's only going to last another like 4 or 5 or 6 billion years. So whatever star system, whatever solar system was here 10 billion years ago, died. Like, that star extinguished its lifetime. Like, it burned up isn't the right term. Maybe fusioned up is the better term. But that star died, and one of the deaths of a star results in an explosion. What's that kind called? Supernova. It's called a supernova. I don't know if there's a regular nova. I'm not sure about that. Yeah, I've never quite heard of a regular nova. There must be, right? Maybe a regular nova is when it doesn't explode, or I don't know, probably not. But yes, so a supernova is what you call it when a star explodes. It doesn't always happen, but it can happen, and that did happen to our previous version of our solar system. So what we ended up with after that supernova was just a huge cloud of dust. So this, I think, is a photograph. Do I have a caption on it? Yes. This is a photograph of a nebula. A nebula is just like a big dust cloud. This obviously would not be the nebula that became our solar system because we didn't have cameras, 7 billion years ago. But this is some other exploded star. So that's what our solar system was, kind of in between the previous star that used to be here and our sun. And then what do we know happens to matter when it's in the vicinity of other matter? Right? Gravitation. Right? Gravitation. So this cloud of matter, this cloud of dust and gas molecules and chunks of maybe rock stuff, like fist-sized stuff, it's going to start kind of caving back in on itself. Going to start coalescing into larger chunks of matter. So most of the matter would kind of end up coalescing kind of back in the center. Right? There'd be more matter when the old star exploded, there probably would be more matter in the center. So what did that matter become over the course of a couple 100 million years? Starts with S. What's that? Yeah, the sun, right? So the stuff that was in the highest concentration of matter, that is now the center of our solar system, is what our sun became. Maybe I even drew that too small. Maybe it would be more like this stuff. Went all the way in towards the center. Now, there's other stuff out here, and this is not a uniform density at all. In fact, I could even see things like loops and whatnot. So let's just focus on this little, can you, from where you're sitting, see this little loop here I'm talking about? All right, well, if you can, great. If not, sorry. If I'm a piece of dust right here, I'm probably not going to get sucked into the middle and become part of the star. I'm probably going to get sucked to the left and become part of this kind of high density region of matter that's over here. And I'm not going to end up ever going anywhere near my star. Well, that might not be true. As long as I have a tangential velocity that would keep me in orbit, right? I'll probably never come anywhere near the center of the solar system. What might I become? What might like this chunk become? Like if we're talking about our planet maybe, but like if this was our solar system 7 billion years ago, what would maybe this be? I don't know about an asteroid. That's going to be a lot of mass. I mean, maybe that is going to be Saturn. Maybe that is going to be Neptune. I think that probably would be something pretty big. That's a lot of matter right there. That's going to kind of clear out that region of space. So anyway, it is possible that all this stuff could end up going into the center if we didn't have a tangential velocity. And that would be a very boring solar system. We wouldn't have planets. We wouldn't have moons for some of these planets. But we do think that maybe just about all is too strong. The vast majority of the star systems in the galaxy and in the universe do have planets, right? Because when these supernovas explode, there is complexity, and we don't just have a uniform mass distribution, right? So our solar system has gravity to thank for allowing a bunch of mass to come together pretty far away from the star, right? In what we call the kind of habitable zone. It's not too hot, not too cold. We can have liquid water there. So that's what gravity does on one large scale. There's some other scales that we might consider. What I'd like to do is show you about a 6-minute video clip, kind of talking about the exact same stuff that we just said, and then take questions that you have after that. All right, so this video clip, I think it's from some sort of like popular Discovery Channel show. It's not one that I've really watched there.
Our solar system, the place we call home, lies about 26,000 light years from the center of our galaxy, the Milky Way. Or around 2/3 the way out. The story of how these huge planets came to be orbiting an average yellow star is 6 billion years long. And since we don't have that much time, I'll speed it up a bit. It starts with a bang.
So that's the old star that
Long
exploded.
ago, an ancient star exploded, littering space with swirling clouds of the materials it had made while it lived, and the heavier metals it created as it died. We know this because we can see similar fields of dust out in space today. They are called nebulae, and they are very beautiful. Every nebula is different, and in our case, the clouds contained nitrogen and oxygen and iron and silica and all the other stuff needed to build a world like ours. Then the tireless force of gravity started to pull it all back together. And the heavy engineering that produces planets began.
Right, so we can see some coalescing of small stuff into bigger stuff now.
Vast spirals of dust began to form. And at the center of one of these, a rocky planet called Earth started to take shape. Built of stardust and assembled by gravity. Fast forward 100 million years, and it had grown into a giant ball, sweeping up billions of tons of celestial debris. This is where the Earth came from, and therefore how you and I began. But our planet would have remained a large, sterile ball of rock and metals, minerals forever, were it not for one more event, one more expression of the forces of nature. 93 million miles away, at the heart of the giant nebula, the pressure and temperature of a ball of hydrogen gas had become so great that the atoms were beginning to fuse. A new star, our sun, was coming to life. As the sun ignited and gave off a huge blast of solar wind, a radioactive gust of energy. This blew all the remaining dust and gas that was left over from the nebula out to the edge of the solar system, which is why everything is nice and orderly today. In the outer reaches of the solar system, we have the huge gas planets, Jupiter, Saturn, Uranus, and Neptune. Further in are the denser, rockier planets, Mercury, Venus, Mars, and of course, the Earth. Lucky for us, the Sun is 865,000 miles in diameter, or just the right size to burn consistently for a very long time. 8 billion years. Long enough to allow the next development to take place. Life.
Alright, why did I write that on the board? Outer reaches of the solar system. Who was there? Who did they say was there? Yeah, Jupiter, Saturn. Why did I write that down? Because I really liked it or really didn't like it?
You don't like it.
I don't like it. I don't like it. Why not?
It's indefinite.
Because what?
It's indefinite.
Oh no, it is definite. It might not be possible to pinpoint the exact edge of the solar system, but you know, we have other solar systems that we'd have to have the edge of ours somewhere in between. So there's some other reason I don't like it. Alright, let's take a look at the image I had up here, which was a silly image, right? But we have, what is the green, Mercury. I don't know why Mercury looks like that. I don't know why Venus is a cherry. I don't think these are supposed to match up at all. Maybe in size slightly. No. Mercury, Venus, Earth, Mars, Jupiter, Saturn has a ring, so that makes sense. Uranus, Neptune, Pluto. Pluto's the furthest thing away?
Yeah.
No. No. Pluto's pretty far away. And sometimes, in fact, sometimes Pluto's not so far away, right? If we can believe this figure, then Pluto, and I know that it's true, Pluto is oftentimes closer than Neptune to the Sun. And Pluto is just one example of a whole bunch of objects called Kuiper Belt objects. There are lots of things out past the planet part of our solar system. And then there's other stuff out further away. Anybody know the name of the stuff that's further away but still part of our solar system? It's called the Oort cloud. Right? And that's really, that's way far away. So our solar system, yeah, I'm just going to say pretty big also. That's what some of you guys said. Solar system pretty big, but it's much bigger than we often give it credit for when we're just thinking about Mercury through Neptune or Mercury through Pluto. Now, there was an additional reason given for space being a vacuum besides just gravitation, and it's not something I hear frequently, but then we were introduced to that solar wind, or that blast of solar wind, which it said push stuff out. I've actually never heard of that other than this video, but I bet you that it is true, or at least partially true. Alright, so anyway, it sounds like some of you are ready to move on. Are there other questions, though, from you guys right now about our solar system coalescing from a big cloud of gas due to gravity. I'm not ready to really go beyond gravity still. We looked at this last time, right? Good, because I don't want to do it again. But I want to remind us of this. So what was this? We combined our gravitational force and our centripetal force and said that the speed of something that goes in a circle, so the speed of one of our planets, only depends on the mass of the star that it's going around and how far from the center, or how far from the star it is. Astronomers had a slight problem with some data agreement. Right? Some of you guys are having problems with data agreement with your centripetal force lab. Well, astronomers in the last decade had some, maybe a little more than that, 15 years ago, had some problems as well. Who's this? Probably not the Milky Way. If it's a photograph, it's definitely not the Milky Way. Right? It's some other spiral galaxy. In fact, I see hints from some angles of a spiral barred galaxy. Right? But that's some spiral galaxy. And one of the reasons it's spiral is that it is like spinning. Right? The whole thing is spinning. Everything in it is spinning. And these arms kind of show us the direction of the spin. So this galaxy, from our perspective, would be spinning like clockwise. And we can actually get a pretty good sense of how fast stuff is spinning. It depends a little bit on the orientation of the galaxy to us, but we can actually make pretty good measurements of the speed at which stuff is moving out here. And astronomers found that it was actually too fast. Right? The stuff in the arms of these galaxies was spinning faster than it ought to be, based on how far from the center of the galaxy and how much mass is in that galaxy. So who already knows, who can tell me, raise your hand, don't say it out loud, but who knows what they pinned that discrepancy on? Oh, this is new for everybody. Henry, you don't know either? No. All right. Now, this is not the only line of evidence for this stuff, but it's a major line of evidence. Dark matter. All right? So not regular matter, but matter that has mass but doesn't interact with light. All right? So we can't see it. We can feel it gravitationally, but we can't see it. It doesn't do light. All right? So dark matter, right? This is one of the major arguments for it. And not only, like, can we just say there is dark matter? There's actually way more dark matter than there is regular matter, like by a lot. Here, I hate, I like scatter plots. It's very rare that I like pie graphs or bar graphs or whatever, but in this case I like it. So ordinary matter, right? That's the stuff that makes up all the atoms that we deal with, and that's 4% of the total energy of our universe. Dark matter, right? This stuff that we can feel gravitationally, but we can't see like with our eyes. 4 to 5 times more. More of that stuff than we have of ordinary matter. All right? Kind of weird, but this is accepted. Like, nobody doubts that that's real. Yeah?
Like on our planet, is it still the same ratio, or is it?
Oh, no, we believe that we just have regular matter. Yeah, we believe that I think, that's my understanding, is no, we think we are made of ordinary matter. Yeah. Ollie.
When you say dark, do you just
Yes.
mean like sunlight or just anything, any type of light known, but we can't see it?
So dark matter doesn't do photons.
Okay.
Doesn't do visible light, doesn't do X-rays, doesn't do microwaves, doesn't do any of the kind of light that we can see, whether it be our eyes or detection devices. Other issues with dark matter. Yeah, Bert.
How are they affected? They can't affect it? Or is it
Gravitational.
Is it just like Newton's constant? It's a big point,
No, I don't. Oh. Ask me that in a different way. I'm not sure what you're asking.
Never mind.
Sure?
Yeah.
So I might be able to answer it.
I'm just saying, like, the other day you said Newton chose his gravitational constant.
There are far deeper reasons than this that the gravitational constant is still just a fudge factor and not a physical measurable thing. Because there's another slice of this pie, right? There's another slice of this pie which is actually 3/4 of the energy of the universe. So 4% of the energy of the universe is in the form of like ordinary stuff. Right? 20% is this weird stuff that does gravity but that doesn't do other things. And then 3/4 is the stuff that we call dark energy. This is what the Nobel Prize was given for like 2 years ago. We have a very big problem in the universe related to gravity. All right, so we are a galaxy, and we said earlier in the year that there are, you know, trillions of galaxies in the universe. And we talked for a minute about how the universe started, but we haven't said anything about what the universe has done since then. All right? So what is the universe doing today is a pretty weird thing. So what is the universe doing today? Two of you that have watched have watched a few shows on this. Alec, what is it doing today? Expanding. Right. Is that a problem?
Yes.
It's not necessarily a problem. It's a little bit weird, but it's not necessarily that big of a problem. All right. I am drawing a circle. I'm not trying to imply that the universe is a sphere. It's not. But I'm drawing a circle because I don't know what else to draw to show the whole universe. And I'm going to draw dots, right, to just represent some of the many galaxies that are in the universe, right? I have to draw about an Avogadro's number worth of dots in order to get the actual amount, but I'm just going to do a bunch. So we know 15 billion years ago that all of this stuff was right here at a spot smaller than the size of an atom, and it exploded. Right? So we had an outward velocity for sure. If we did a free body diagram on this galaxy here, what would it indicate? Point with your fingers what the direction of the net force would be on this galaxy right here. Oh, I'm seeing some bad points. Bad points. There would be about 40 individual gravitational forces acting on it, and the sum of that would all be this way, wouldn't it? Right? Because this one's pulling on it this way, this one's pulling on it this way, this one's pulling on it that way, this one's pulling on it this way, most of the stuff is pulling on it this way. There's a couple things that might be pulling some other direction. But all, maybe 95% of the Avogadro's number worth of galaxies in the universe is pulling it this-ish way. So this should have a net force that's kind of bringing it back to the center of the universe. Now, we could be moving out and slowing down, and that could be fun, right? Because if we still had some of the inertia from the Big Bang bringing this thing this way, it could be accelerating towards the center and just not have lost its outward velocity yet. And that's what we kind of thought was happening from like the 1960s, maybe through the early 2000s. And then what was discovered in the 2000s, that kind of was very weird. Well, dark energy was a proposed solution to the problem, but no, we have a problem that dark energy was invented to solve. The problem is that not only are we moving outward, we're actually speeding up while moving outward. So the rate at which the universe is expanding is increasing, getting faster and faster and faster. And that is super, super weird, because gravitationally, everything should be collapsing back in on itself. And we're doing the opposite of that. All right? So the best theory, and the theory that most people do accept, the best theory for this outward propulsion today is dark energy. And I don't really think that there's anybody on the planet that really feels like they have a good intuitive sense of what dark energy actually means. You can hear explanations. Did you watch, have we watched any of the kind of substitute videos that I showed? No. So there are a number of videos that I show when I'm out sometimes that involve this stuff, and you'll hear a couple of explanations, but nobody claims to really understand that stuff. Nobel Prize 2 years ago, right, for the data that told us that the universe is expanding outwards, right? Major area of research in theoretical physics today. You're welcome to ask me questions about dark energy. I can pretty much promise you I can't answer them, but you're welcome to try. Because I think this would mark the end of what I want to say about gravitation and Kepler's laws. So follow-up questions on this stuff before we move on. Yeah.
What's your best explanation of it?
My best explanation is that there is something called vacuum energy, which is energy that just empty volumes of space have, which I can't really back up or defend whatsoever, but that seems to be the most common thing that's talked about when trying to explain this. That a totally empty region of space, no matter whatsoever, actually does have some energy ingrained in its fabric. How
So like that energy, like in theory, does that energy come from something else, or is
does
it
that
just
energy,
there?
does the vacuum energy come?
Yeah.
Yeah, sorry.
Okay.
Does the vacuum energy come from something else was the question?
Okay.
Yeah, no, wrong guy, sorry. Anything else? Okay.
No, wait, actually.
Yeah.
So if everything in the universe, Big Bang, is at one place.
Yes.
Now it's all out there. It's accelerating outwards away
Right.
from it. Do we know where the Big Bang happened? Like
Do we know
towards
where the Big Bang happened? I don't know how good our mapping of our galaxy or even universe is. I mean, there are maps. In my head, it would be the geometric center of our universe. I can't think of any flaw in that logic. Do we know where that is? I'm not sure. I'm not sure. I would imagine so, but I'm not so sure. Anything else? All right. So let's see. I think we already said just about everything I wanted to say about January. Why don't we take a brief look at our project? I would love to do 5 minutes of Chapter 8, but I'd actually rather take a look at our project first. So I'm sure some of you already read through this since I emailed it out a few days ago. Some of you, helped me refine what I said about this after our test the other day. But our challenge is to build something to put an egg into that will survive the fall.
All right, seniors, we're going to be taking our picture outside. Please come down and gather into NPR for further directions. Thank you.
You guys want to get a picture?
No.
All right. So let's end a little bit early to help us kind of get mentally ready to represent. But I do want to at least say a few things about the project for the folks that haven't looked at this yet. So you need to build something that you can put an egg into that when I drop it from pretty high, it won't break. The hardest part of this is it's got to fit into a quart-sized Ziploc bag. That's not the big ones. The big ones are the gallon-sized ones, right? So it's bigger than a sandwich bag, but not as big as a huge one. Yeah.
So, can you correct me if I'm wrong about this?
Okay.
So is it you fill the bag with things and then drop the egg in the bag, or you make something and then
That is not. So the question is, are you supposed to just bring stuff that you're going to put into the bag and then slip the egg into that? That wouldn't violate any rules, but I don't think that's the way to go. Because then what if the egg is up against one side of it and that happens to be the side that hits the ground? That doesn't seem like a wise way to go to me. What I would envision is you're designing some contraption that doesn't need the bag. I'm just using the bag because I don't want to clean up a mess. For the break. That's the whole purpose of the bag. So that's not what I'm envisioning. All right. So I'm giving you some suggestions of materials that you might use. You can use whatever the heck you want, as long as you can't use liquids. I think I said somewhere. And you do actually get extra points if for you having a low mass device. So obviously you don't want your egg to break, but for purposes of competing against each other, a crack is not as bad as a fully broken eggshell. Now, I think what I never said on here at all is, what the heck do you get if you win? So I'm just going to do the same thing as our first marking period project. The 2 teams that have the best score for this are going to get 1 point extra credit on, if I can do it, the second marking period grade. I think I should be able to do that. I'm having a slight reservation about doing that before your presentations. On the back, I see some hands, I'll get you in a minute. Right on the back, I do give you a list of due dates. It's possible that I messed up. I don't know that I included